When we talk about sets, it's natural to try to compare sets in some way. We've seen sets that are equal to each other where they're just listed in a different order, but we can also see that some sets are contained in some sense in another set. For example, that set E, which was all of the even natural numbers, is contained in the set N, which is all the natural numbers. And so to sort of formalize that idea, we have a subset. So we say that a set A is a subset of another set B if every element of A is also an element of B, right? And we use this notation A is a subset of B. That's what this notation means. It looks almost like a less than or equal to sign, but it's more curved. All right, so this is saying A is contained in B, or A is a subset of B. In other words, every element of A is also an element of B. So let's look at some examples here. We have the sets A, which consists of the elements 2 and 3. B consists of 1, 2, and 3. And C consists of 1 and 4. So do we have any subset relationships here? Well, yes, right? We have the elements of A are just 2 and 3, and 2 and 3 are also elements of B. So that means that A is a subset of B. But B is not a subset of A because it's not the case that every element of B is also an element of A. For instance, 1 is an element of B, but not an element of A. So we could say that B is not a subset of A. So you can just put a slash through it to say not subset. All right, let's consider C. So C contains 1 and 4. Is that going to be a subset of either of these? Well, no, it's not a subset of B because it contains the element 4, which is not an element of B. And similarly, it contains a 1 and a 4. It really has nothing in common with A, so it can't be a subset of A either. And so we maybe think that C is not a subset of anything here, except technically you can say that C is a subset of, C. C is a subset of itself. Why? Well, remember the definition is A is a subset of B if every element of A is also an element of B. So C is a subset of C if every element of C is also an element of C. Okay, that seems kind of trivial. Of course it is. In fact, that means A is also a subset of itself and B is also a subset of itself. Any set is a subset of itself by this definition. All right, now, how about the natural numbers and the integers? Remember from the last video, this means the natural numbers, the positive whole numbers, and the integers is positive and negative whole numbers along with 0. So is n a subset of z? Well, we want to check that every element of n is also an element of z. So 1, 2, 3, etc. Is this a subset of 0? Plus or minus 1, plus or minus 2, etc. Is that true? Yeah, right? 1's an element of z as well. 2 is an element of z as well. 3 as well, etc. So this is a yes. Okay, is z a subset of n? Well, no, right? We can see, just sort of looking at this example here, we have that 0 is an element of the integers, right? 0 is an element of z, but 0 is not an element of the natural numbers. And that's all you need to show that one set is not a subset of another. You just need to find one element in the first set that's not in the second set. So we could say 0 is an element of z, but 0 is not an element of n, and so z cannot be a subset of n. All right. Now, two sets we would say are equal if they contain the exact same elements. In other words, right, i.e., that is, if A is a subset of B and also B is a subset of A. If everything in A is also in B, and if every element of B is also an element of A. As an example, well, you could say, let's say this set A, call it 2 and 3 from above. This is the same set as 3 and 2. Okay, right, so we don't have any other examples on here of two sets that are equal to itself, although you could say something like A is equal to A or B is equal to B, etc. But in particular, we have that for all of these three examples here of subsets, it's also the case that they're equal to each other. C is equal to C, A is equal to A, and B is equal to B. And so sometimes we want to say that one set is a subset of another, but they're not equal. They're not just the same set. And so in that case, we describe them as proper subsets of each other. So we would say that A is a proper subset of B if A is, first of all, it has to be a subset of B. In other words, everything in A has to be in B, but they're not equal. So that is to say, A is a subset of B, but B is in some sense bigger. It has at least one element that's not an element of A. And in that case, we would write that A is a subset of B using this notation here. We take away the line underneath, right? It's sort of like a strictly less than symbol, except it's a strict subset symbol. So from that example up above, where we had that A was 2, 3, and B was 1, 2, 3, right? It's true that A is a subset of B, but it's also true that they're not equal. B has an element, namely the element 1, that's not in A. So A is a proper subset of B, right? Anytime you're a proper subset, you're automatically going to be just a regular subset. But the converse of that is not necessarily true. All right, other examples, the natural numbers are a proper subset of the integers, because we had seen that n was a subset of z, but z is not a subset of n, right? They're not equal. Okay, now, sometimes it's useful to talk about all the different possible subsets of a particular set A. And we call it the power set of A, and we use this sort of cursive P of A to say the power set of A. So the power set is just all possible subsets of A, joined together in one big set. So let's look at an example. If A is a set that contains the elements 1, 2, and 3, the power set of A is just a set containing every single subset of A. So the elements of the power set of A are themselves sets that happen to be subsets of A. So I'll give you an example. The number 1, and it's its own set, right? The set containing 1 is a subset of A. Right? Check and confirm that this set is a subset of A. Of course, right? The only element of this is 1, which is also an element of A. Similarly, the set containing 2 is a subset of A. The set containing 3 is a subset of A. Are there others? Yeah, right? We could pick out, let's say, 1 and 2. So the set containing 1 and 2 is also a subset of A. The set containing 1 and 3 is a subset of A. The set containing 2 and 3 is a subset of A. And is that it? Oh, well, remember, we had said technically every set is a subset of itself. So the set containing 1, 2, and 3 is also going to be a subset of A, right? A is a subset of itself. So is that all? Well, there's one sort of minor technical detail here, which is the empty set is going to be a subset of every set. All right, so I'm going to add the empty set in here, and that's going to be our last element of the power set. That's the last subset of A. So why is the empty set considered a subset of A? Well, technically, the empty set is a subset of every set. And that's true because to check that this is correct, that the empty set is a subset of A, we need to check that every element of the empty set is an element of A. Well, there's nothing to check because the empty set has no elements. So this is sort of trivially true, that every element of the empty set is also an element of A. Right? Another way of thinking of it is, if this wasn't the case, if the empty set was not a subset of A, then you would have to find some element of the empty set that was not an element of A. You'll never be able to find that counterexample because there are no elements of the empty set. So the empty set is really considered a subset of every set. This is maybe an important one that's going to come back. The empty set is a subset of every set. All right, now, it's useful sometimes when we're talking about all the subsets of a particular set to have some kind of a shorthand because we don't like having to draw out all these curly brackets, right? This is sort of annoying to do. And so conveniently, we can use a bit string or a binary string of zeros and ones, to encode a subset of a finite set. So as an example, let's say A is the set 1, 2, 3, and 4 now, the set containing 1, 2, 3, and 4. For any given subset of A, we really have to decide whether each of those 4 elements, 1, 2, 3, and 4, is in the subset or is not in the subset. And if we record those decisions with a 1, in the case that it is in the subset, and a 0 in the case that it's not in a subset, it's going to give us a binary string of length 4, which we can use to then translate into subset. So as an example here, let's look at 1 and 4. Right, remember there's 4 decisions to make here. Is each one of these numbers in the subset or not? All right, the first one is 1. Is 1 in the subset? It is. So we'll put a 1 here for yes. The next number in our set is 2. Is 2 in the subset? It is not, so I'll put a 0 here. All right, 3, is 3 in the subset? No, so I'll put a 0. And 4, is 4 in the subset? Yep, so I put a 1. So this is going to correspond to the binary string 1, 0, 0, 1. Similarly, 2, 3, and 4, the set 2, 3, and 4 is a subset of A. Is 1 in the subset? No, so put a 0 in the first spot. But then 2, 3, and 4 are all in the subset, so we'll put 1s in the remaining 3 spots. So this is saying, I'm not going to include 1, but I will include 2, 3, and 4. All right, my third subset here is just containing the number 3. So it doesn't contain a 1, it doesn't contain a 2, it does contain a 3, so put a 1. It does not contain a 4. And finally, the empty set, what is this going to correspond to? Well, remember, the empty set can be thought of as a set with no elements. So is 1 in this set? No. Is 2? No, right? 3 is not, and 4 is not. Nothing's in here. So this would correspond to the binary string 0, 0, 0, 0. And it works both ways, right? I could give you, let's say, 0, 1, 0, 1, for instance. If I gave you a binary string of length 4, you should be able to figure out what subset that corresponds to just by sort of remembering what each entry corresponds to. So this having a 0 in the first place means that the number 1 is not going to be in the subset. Having a 1 in the second spot means that 2 is in the subset. A 0 here means don't include 3. And a 1 here means we do include 4. So this would correspond to the set 2, 4. And we'll see that thinking about subsets as binary strings can be really useful in some counting problems in the future.